What if you could work with some of the world's most innovative companies, all from the comfort of a remote workplace? Andela has matched thousands of technologists across the globe to their next career adventure. We're empowering new talent worldwide, from Sao Paulo to Egypt and Lagos to Warsaw. Now, the future of work is yours to create. Anytime, anywhere, the world is at your fingertips. This is Andela.
Welcome to Dissecting Channels, Slices, and Maps in Go. We are going to talk about the most commonly used building structures in Go: slices, maps, and channels. We probably all know how to use them, but not necessarily how they work under the hood. In this talk, we are going to follow an experimental approach to analyze how they behave in memory when we modify, create, or access these structures. Okay, we are going to need some class materials: the scalpel, the microscope, and the subject. Let's start with the slices. What is our scalpel in a slice? We are going to use a function called scalpel that is going to receive a slice. In this case, I'm going to use a slice of integers because it's simpler. And I'm going to use unsafe to get access to the memory address of the slice and store that data in a structure. Then I have a microscope function. The microscope function is going to show me the data in a readable way to analyze what is going on. And the subject, in this case, is a slice. A slice is not other than an array or one or more slices. We are going to see what I mean. This is the structure of a slice. A slice is an array. It's a pointer to an array in memory, just a chunk of memory in the heap. In this case, is a chunk of memory that stores integers. Then I have the length and the capacity of the slice. What happens when I create a new slice of integers? In this case, I'm creating an empty slice of integers. The array, the memory address is not especially important here because we are not storing anything yet. The slice length and the slice capacity is 0, and the stored data is just an empty. It's empty. Okay, what happens if I append a new integer? I'm going to the slice code is going to reserve a chunk of memory to store that integer and store there the integer value. In this case, 1. The slice length is 1 and the slice capacity is 1. Let's see what happens when I add more data there. If I add 4 more elements, it's going to change the memory address. Why is changing the memory address? Because I don't have enough space in the original reserved memory. If I go here and see the slice capacity, when I added 1 element, the slice capacity is 1. So I'm not able to store more data in that array, because the slice capacity is saying the amount of data that is able to store that array in memory. In this case, it's 1. So every time that we reach the capacity limit of the slice, it's going to happen a resize. A resize is just reserving a bigger chunk of memory in the heap and migrating all the data to this new chunk of memory. In this case, we added 5 elements, and in that process, the slice has been growing. The slice is not going to grow 1 element at a time. The slice capacity is going to grow more than 1 element normally, because you don't want to resize the slice with every single insertion. So in this case, at some point, I added enough data to grow the slice, and the slice grows to the capacity of 8. That means that I reserve a memory for 8 elements, but in this case I'm only using 5 of them. So the stored data in memory is 1, 2, 3, 4, 5, 0, 0, 0, because I have 8 positions in memory, space for 8 integers in memory. Okay, what happens if I create a subslice? A subslice is just a slice of a slice. In this case, I'm creating a subslice from the position 1 to the position 4. What is interesting here is the memory address. You can see that the memory address here is C00001A540. And here the memory address is C00001A548. That 8 is because we are using integer, and in my architecture that means integer 64, what is 8 bytes. So because this is the same, actually it's the same memory, the same chunk of memory, but 1 byte after, 8 bytes after. 8 bytes after because I'm starting in the position 1. So I'm skipping the position 0 of the original array or the original slice. And also it's interesting the slice capacity because it's exactly the same chunk of memory. The slice capacity is 7 because before was 8, but I'm not able to use the whole array. I'm just able to use the rest of the array, the memory that is reserved from the address that I'm using. Okay, let's see what happens if I modify a subslice. If I modify, for example, the position 0 of the subslice, that is the position 1 of the original slice, what is going to happen is the original slice also gets modified. It gets modified in the position 1, and the subslice is modified in the position 0, as I did in the code. Okay, what happens if I append something? That is even more interesting. I'm appending 6, the value 6 to the subslice, but the subslice was from position 1 to position 4. It is just 3 elements, and is adding a 4th element at the end. But the end of the subslice is not the end of the original slice. So we are overwriting the 5th position in the original array, and we are appending in the slice. So the behavior from the perspective of the original array is different and the behavior from the subslice. As you can see there, the value 6 is affecting both the subslice and the original slice. Even more interesting is if I append more data and then modify something in the subslice. If I append more data to the original slice and modify something in the subslice, what I get is we are not because I added enough data to trigger a resize in the original slice. We are no longer sharing the memory, the array memory address. We are pointing to a different chunk in memory, so that generates a disconnection between both slices. So this as a subslice can be considered a window to another slice if that slice hasn't been resized or the subslice hasn't been resized. That is probably a very unexpected behavior, so I wouldn't try to relay in this behavior for anything. Okay, I have the code that I used to run this experiment here. I have a link at the end of the talk with all the code. So if you want to reproduce the experiment, you can. So just check out the link at the end of the talk. Okay, let's talk about maps. The scalpel for maps is going to be pretty much the same. I'm just using unsafe to access the memory and store that memory in a structure. In this case, as an example, I'm using a map of integer values and integer keys because it's simpler. The microscope is more complex because the data structure in maps is way more complex than the data structure in slices. And the subject is the map. A map is just a set of map metadata and a set of buckets. That is where the real data, the data that you store in the map, is stored. Okay, what is the structure that stores a map? Well, we have the count, that is the number of elements in the map. We have the flags, that is not important for this talk. We have the b-value that represents the number of resizes of the map. Well, it's related to the number of buckets, not super important, but yeah, it is related to the number of buckets. The number of overflows gives you an approximation of the number of overflow buckets. The hash zero is a completely random number that is generated whenever you create a new map. And this random number is used to generate the hash of the keys to decide where the keys are stored in the map. This is interesting because this gives the certain feature to the maps that it is not predictable where the keys, in which bucket the keys are going to fall. It's not predictable before you create this random number, before you instantiate the map. So you can't relay in the order of a map or things like that. Or in what, yeah, the order of a map is not reliable in Go. One of the reasons is because the hash zero. The buckets is just a pointer to a chunk of memory that stores a set of buckets. We are going to see what a bucket is right away. Then we have the all buckets, that is another pointer to the same, to another chunk of memory storing buckets again. And evacuated is the number of evacuated buckets. We are going to talk more about that later. And some extra metadata that is not super important for this talk. We have the bucket struct also, that is the structure that is stored in the heap, storing the real data. Each bucket is going to contain 8 elements, and is going to have a top hash that is just a set of chunks of the hashes of the keys stored in the bucket. Well, not especially important for this talk either. And then we have the keys and the values. The keys and the values are 2 arrays of 8 elements storing each key and each value. Each position in the keys correspond to the same position in the values. And then we have the overflow pointer. The overflow pointer is another pointer that points to another memory address that contains a bucket, an overflow bucket. We are going to see what an overflow bucket is later. Well, let's start creating a map, an empty map. In this case, I'm creating an empty map with integer values and integer keys. The map size, because the map is empty, is going to be 0, the flag 0, the b 0, what is the for 0 size. Well, the b0 means that there's only one bucket. The hash it, that is a random number, the number of overflow buckets is 0. The initial, the buckets is pointing to a chunk in memory that is storing an empty bucket. An empty bucket means basically top hash 0, all the keys are 0, all the values are 0, and the overflow pointer is null or 0 in this case. The all buckets is not pointing anywhere, and the number of evacuated buckets is 0 for now. Okay, what happens if I add one element to this map? If I, for example, store in the key 1 the value 10, now the map size is 1, and everything else keeps the same except for the bucket. If I go to the bucket, I see that I store one key, that is the key 1, and one value, that is the value 10, both in the same position in the keys and the values array. The top hash is just a chunk of the key of the hash of the key, but it's not super important. Okay, let's keep going. If I add more data, in this case I'm adding 8 more elements, eventually this is going to trigger a resize. In this case now the map of the map size is 9, the b is 1 because this number of elements has triggered a resize. When a resize happens, it's going to reserve another chunk of memory, and it's going to migrate all the data from, well, it's going to migrate the data from the original bucket to the new set of buckets in memory. Normally normally duplicates the number of buckets each time, and in this process of migration, it's going to evacuate the old bucket. That means pick all the keys and the values and store in the corresponding bucket in the new set of buckets. That implies that the keys have to be, it needs to recalculate the hash to decide where it's going to fall in the new buckets. Again, the number of evacuated buckets is going to be 1. In this case, because the old bucket was evacuated and moved to the new buckets. As you can see here, the elements doesn't need to be the same of the old set of buckets. What an overflow bucket is. The maps gets resized when it reaches certain threshold, but can happen that you have a map with some data that is not enough to justify a resize, but one of the buckets is completely full. And then suddenly you try to add something and it's going to fall in that bucket, and instead of triggering a resize, a simplest approach and better approach to optimize the usage of the map is just create an overflow bucket that is going to store, is going to reserve a chunk of memory to store a new bucket, and is going to store in that bucket the new key, and link that to the existing bucket. In this case, as you say, the bucket 1 have an overflow pointer that points to another bucket in another position in memory that have just more information related to the bucket 1. And also you can see that the number of overflow buckets is now 1. What happens when you have big resizes? When you have big resizes in Go, what it does is using these buckets and all buckets variables that are pointing to memory addresses. So what it does is reserve a new set of buckets, doubling the size of the number of buckets, and start migrating the data to that buckets. That new buckets is going to be buckets, and the previous existing buckets is going to become all buckets. And it's not going to migrate all the data in one time, because that will take extra time, that can have some performance impact. So what it does is just start migrating the data gradually with each operation. This way, you don't have a big block when you need to resize a map. You have just resize the map, and it's not blocking that much, and it's just getting some performance degradation during certain time. And whenever everything is migrated, the map backs to normal. The buckets, all buckets, and number of evacuated buckets is used for this process of migration. Once all the buckets in the old buckets are evacuated, the system just releases that memory. Okay, here is the code. If you want to reproduce that, you're going to find them at the end of the talk. Channels. For channels, I'm going to use a channel of Conf42. Again, just a using unsafe to access the memory, storing that in a structure. The microscope, more or less the same, getting that structure, printing that in a readable way. The channel, the subject in this case is a channel. More specifically, I'm going to use the buffered channels because it's more interesting, and you can infer how a non-buffered channel works, basically not assigning a buffer of 0 to this, and you are going to have exactly the same behavior. You can infer the behavior based on that. A channel is going to have a queue count, that is the number of elements stored in the buffer, a data queue size, that is the number of elements that the buffer can store, the buffer itself, that is just a chunk of memory. In this case, is a chunk of 4 positions of int32 because it's a buffered channels with size 4, and the channel type is int32. The element size is the size of each element in the buffer. The closed defines if the channel is open or closed. The element type is a pointer to, in this case, int32 representation, so it's a pointer to the type that is stored in the channel buffer. The sendx and receivex are two indexes that points to the position in the buffer that is going to be the next place where you send something or where you receive something. The receive queue and the send queue is a 2 wait queue list. A wait queue is basically a place where you can store goroutines that are waiting for something. So in this case, the receive queue and the send queue are where the channels, where the goroutines wait for the channel to have data or to have a space for data. Okay, let's see an example. If I create a channel of int32 with 4 positions, with a buffer of 4, what I'm going to have is a queue count of 0, a data queue size of 4 because I have a space for 4 elements, and the element size is going to be 4 because it's an int32. That means 4 bytes. The buffer is going to contain 0, 0, 0, 0 for now because it's just a 4 positions buffer of 4 integers that is no elements yet. Okay, what happens if I add 1 element to the channel? If I add 1 element to the channel, the queue count is going to be increased to 1. Because I'm adding a 5, that 5 is going to be stored in the buffer where the sendx index was pointing to. The first position in the buffer, so I store 5 in the first position in the buffer and increment the sendx to the next position in the buffer. What happens if I add more data than the buffer can store? In this case, I'm adding 4, 3, 2, 1. If I add 4, 3, 2, 1, I'm going to add 4 in the sendx position. That was the second position. The sendx is going to be increased, and I add 3, and then I add 2, and so on. But whenever I try to add the 1, the queue count is already 4. So there's no enough space for adding a new element. So what the goroutine is going to do is going to store himself in the send queue, and it's going to park himself to wait until there is some space in the buffer. What happens if somebody reads something? If somebody reads something, it's going to receive that 5 because it's going to read the data in the receive X position. That was the first element in the buffer. So it's going to read that data and return that data to the requester, and it's going to increase the receive X. The data queue size hasn't changed, but hasn't changed because once we read that data, we see that the send queue have somebody waiting there. So we wake up that goroutine, And that goroutine automatically inserts the one value. The value that was waiting before to try to insert is going to get inserted in the position where the sendX was. And that's the reason why we have still a 4 in the queue count, and the first element in the buffer now is 1, and the receive index and the send index have moved one position. Okay, if I read more data from the channel, what is going to happen is now it's going to decrease the amount of data, the queue count, to 3, because yeah, there's nothing adding more data and there's no more data. Now it's going to read where the receive X was, that is in the second position, so it's going to return a 4, that is what was in the second position before, and it's going to increase the receive X. And that's it. What happens if I read more data than I can that I have in the buffer? Well, it's going to start reading data. It's going to read the 3, the 2, the 1, and when it reaches the point where there's no more data, it's the goroutine that is trying to get data from the channel that is empty is going to add himself to the receive queue and park himself, waiting for new data to come in the channel. If somebody sends something to the channel, it's going to wake up that goroutine. But what happens if I close the channel? If I close the channel, everybody that is connected to receive data from the channel is going to receive the 0, the closed message from the channel. In this case, it's going to go to the receive queue, send that message to any receiver that is in the receive queue, and it's going to change the closed value of the channel to 1. And that's it. Here is the code. If you want to try it, it's interesting. So, okay, some references. If you want to know more about slices, maps, and channels, probably reading the Go runtime code is not complicated. It's not super straightforward, but it's not especially complicated. You can get more or less what is going on. Actually, I wrote this talk just reading that information. If you want to reproduce that experiment, you can go to my GitHub repo, Dissecting Go, and just reproduce these experiments. It's just a lot of fun. And some conclusions. Well, understanding the building blocks of the language is going to help you to understand the implications that building blocks comes with, because sometimes these building blocks have some trade-offs in it, have some decisions that were made by the Go team, and if you understand why that decisions are there and why or how they really behave, you can use it better. Well, also take into consideration that there are some unexpected behaviors that can be surprising, especially the slices one is really interesting. And probably this knowledge is not going to be needed for anything that you are going to do in your work, but it can help in very specific situations. So that's it. Thank you, everybody.